I'm pleased to introduce Dr. Elizabeth Carlton, who is an assistant professor in environmental and occupational health in the School of Public Health. She obtained a PhD in environmental health sciences from UC Berkeley and a master's of public health from Columbia University. She's interested in sustainable control of waterborne diseases and the impacts of environmental change on infectious disease transmission. She'll speak with us today about her work on schistosomiasis in China.
So, thank you to the Center for Global Health for the invitation to speak, and thank you all for coming today. I'm really happy to have the chance to talk about some of the work I've been working on schistosomiasis. This is a photograph of one of the sites I've been studying since 2007. It's an area in southwest China where schistosomiasis reemerged and has really persisted for reasons we don't fully understand. I am an environmental epidemiologist by training, and so I think a lot about how the environment drives disease transmission. And if you look at this image, you can notice a few things. One, there are people coming in contact with water. They're planting rice. People acquire schistosomiasis through dermal contact with water. And you can see bovines being used to plow. Bovines are also reservoirs for the disease. And both people and humans emit the disease in their stool, creating a recipe for transmission. I'm going to talk mostly today about some methods we've been using more recently, merging field-based epidemiology and next-generation or high-resolution genomics to try to understand the reemergence in transmission hotspots. So I'll talk a little bit just generally about global schistosomiasis control programs to give you the big picture. I'll talk about the reemergence and persistence of schistosomiasis in southwest China, the areas where I've been working. And then I'll talk to you about two questions we're trying to answer right now. One, is treatment failure occurring in these regions? And two, where are new infections coming from? So I'll say when I studied schistosomiasis in my infectious disease course in my master's program, I decided this life cycle was far too complicated. I wanted nothing more to do with it. And ironically, this is the disease I've spent the last decade thinking about. Schistosomiasis is a waterborne parasite, and it requires a snail host for transmission. So humans emit the parasite in either urine or stool, depending on the species they're infected with. That parasite is in the form of an egg. It hatches when it reaches fresh water. It infects a snail host. It's species specific. And then the snail life stage is the amplifying life stage. And once it matures, it's released as cercaria, which is the infectious stage to humans. Inside the human host, once people become infected by being penetrated through skin, the parasite matures, it mates for life quite romantically, and begins egg laying. And the eggs are really the source of morbidity. The paired adult schistosome, there's a male and a female here, and they lay eggs, which can cause fibrosis. They cause an immune response, which can lead to fibrosis, anemia. It can impair growth and cognitive development. And more generally, schistosomiasis belongs to a class of diseases called neglected tropical diseases that are thought of as poverty-sustaining diseases. So not only are they found in populations that are impoverished, but they're thought to reinforce poverty by impairing growth and development and work capacity. Schistosoma hematobium, which is found in Africa, is a class 1 carcinogen. It causes bladder cancer. So this is a distribution of schistosomiasis globally. And you can see almost all of schistosomiasis is found in Africa, about 90% of the cases. There are about 230 million people infected globally. This is a very rough estimate because we don't know much about what's going on in many areas. But there are foci in, let's see if I can get this. There are foci in Brazil, and in China, here. And these are two of the regions of the world that are closest to getting rid of schistosomiasis. So in 2012, the global health community banded together and issued what's called the Roadmap for Neglected Tropical Diseases. This is a multinational initiative to really address a class of diseases called neglected tropical diseases through primarily improving access to treatment. And there are two major goals here in regards to schistosomiasis. One is ramping up treatment so that populations all have access to praziquantel, which is the only drug available for schistosomiasis treatment and widespread. It's very safe, very cheap, and very effective. And currently, and I think the current numbers are actually based on a couple of years ago, about 20% of the world's population who's infected with schistosomiasis access. So this is a huge problem, and a problem I'm really not going to talk too much about today, but I want it to be noted. But the other challenge that the roadmap decided to tackle is the issue of elimination. Can we get rid of schistosomiasis in the regions where control has been rolled out? Can we push past just drug distribution into So they are, the global health community is aiming to eliminate schistosomiasis transmission in regions of the world, including the Americas and the Western Pacific region by 2020. Very ambitious goal, and we can talk at the end about whether or not, what the probability of reaching it might be. The case of schistosomiasis in China is a really interesting one. In the 1950s, Mao declared schistosomiasis should be gone. And therefore, they have had a 60-plus year schistosomiasis control program. In the 1950s, there were about 10 million cases in 12 provinces. Today, there are less than 200,000 cases in 5 provinces, and they are aiming for elimination. Schistosomiasis in China is unique in many ways because of this sustained control program. There's an enormous public health infrastructure devoted to schistosomiasis control, which is not true in other parts of the world. And it's a very multidisciplinary control strategy. But many people have their eyes on whether or not China can achieve elimination, because obviously this has implications for elsewhere. So I want to talk a little bit about our evidence for the persistence of schistosomiasis in Southwest China over the last decade. So this study started in 2006 when Dr. Zhang Guo, who's one of my collaborators at the Sichuan Center for Disease Control and Prevention, and Song Liang, who's now at the University of Florida, and their peers discovered that schistosomiasis had reemerged in some counties in Sichuan province where infections had been reduced below 1% infection prevalence, which is thought to be on the road to elimination. And the reemerging areas are noted in the hashed areas on the map. There are 8 counties where schistosomiasis has reemerged. In context, this is China, and this is Sichuan. It's right below the Tibetan Plateau. This is Tibet right here. The headwaters of the Yangtze River are in Sichuan. Are for schistosomiasis. We started a study in 2007 to investigate why schistosomiasis. Our original question was really, why did reemergence occur, and what about the environment might make a region right for reemergence? And we thought this was going to be a very short kind of reemerge and burnout phenomenon. And this shows data from 36 villages in Sichuan. You can see in green are villages where we tested and found no infections. In yellow are villages where we tested and found 1 to 10% infection prevalence. And in red, where we found over 10% infection. So in 2007, this was rather surprising. We knew schistosomiasis reemerged, but we didn't know quite to the extent that we would find infections. We have far more infections than we expected, particularly right around here. We went back in 2008. In 2008, we employed a bias sampling approach. So we didn't test all villages, but in the 27 villages we tested, we found infections in 16 of them. Again, there's this cluster here of infections that we see. And then in 2010, we went back and surveyed all the villages again, and again find 10 villages where infection prevalence exceeded 10%. And this was rather surprising. We went back again. We recently got new funding and went back again this summer and conducted infection surveys in 7 of the original 36 villages. These are biased it's a biased selection that we selected villages where we thought we would find infections, and added 3 new villages. And again, we were really surprised by our findings. We found infections in 8 of the 10 villages. This is a province where it's supposed to be on the edge of elimination. We're almost rid of the disease. And in 3 of these villages, infection prevalence exceeded 10%. In fact, in one of these villages, 27% of the people were infected with schistosomiasis, which, we had, before the infection surveys, my colleague in Sichuan and I had spent many nights awake thinking we were going to get no samples. And we actually had the opposite problem. We got a lot of samples, far more than we expected. So this just shows the same information in a bar chart, but one of the things that's interesting, the x-axis is a village, and you can see in certain villages just persistently we're seeing infections, and for reasons we don't fully understand. We know a little bit about why. We know that some of these villages, they use a lot of night soil, which is the use of human waste as an agricultural fertilizer, great way to spread fecal-borne pathogens around in a village if it's not fully composted. But there's still kind of a puzzle about what is going on in these villages to allow the disease to persist. And it's particularly puzzling given the control program in China. The backbone of the control program globally and specifically in China is the use of praziquantel, which is a drug that can be distributed with minimal side effects to the population. In China, they also use health education. They have been slowly replacing bovines with tractors in areas where this is feasible. This isn't feasible in all areas because some areas are too hilly for tractors to be used. They have had a big push to improve access to safe water in the home to get people, to help people not rely on surface water for washing. There's a snail control program dating back for decades. So killing the snail with glufosinate, a pesticide that kills snails. And finally, and this, is testament to the resources that China has for schistosomiasis control. They've been lining irrigation ditches with concrete. You can imagine this is not inexpensive, but this serves to eliminate snail habitat. And when reemergence was reported in 2006, and when we reported our results in 2007, particularly in these regions, there was a big push to step up the game and control schistosomiasis. The fact that we're still seeing infections in this region is very troubling because there has been, to some extent, a full court press to try to eliminate. So that's a really interesting question. One of the things that's happening in this region that has nothing to do with schistosomiasis is that people aged 15 to 35 are missing, right? They're all gone off to the cities to work in the factories. So we see very few infections in kids. We don't see infections in that middle-aged population because they're gone. And those that we test have low infection levels, but we see a very high infection in the older population. And along those lines, another thing to point out is one of the things we think about with schistosomiasis and other helminths or worms are not just whether or not someone is infected, but how many worms they have in the body. Because the more worms they have, the more morbidity you can see. And this is what you typically see in a highly endemic region. This is a region that the study team I work with started looking at in 2000 in Southwest China. About 50% of the population in 10 villages was infected, and the average person had about 40 eggs per gram of stool, which is a measure of infection intensity. And at each infection survey, we treat people who test positive, and you can see this rapid decline in prevalence, indicated in blue, and in infection intensity. This infection intensity, we think, is a stronger marker of morbidity. So that by 2 rounds of testing and treatment, infection intensity and prevalence was quite low. In the re-emerging areas where we've worked, EPG, or infection intensity, has always been quite low. So we're not seeing a lot of morbidity in this region, but we are seeing kind of persistence of infection. It's not going down, it just seems to be staying stable. So, again, from public health impact, this is probably not a region that has a lot of morbidity due to schistosomiasis, but in the context of elimination, these infections matter because it's not gone. So out of this research, there's kind of two questions that we've been really interested in trying to answer. And I'll say we do not have complete answers to either of these questions, but I'll take you through kind of our path to attempting to answer them next. One, we're interested in whether treatment failure is occurring in this region, possibility. And we can talk about what treatment failure means, because it doesn't just mean drug resistance. And then second, where are these new infections coming from, if indeed we are having new infections in this region? So for the first question, when I was a postdoc, we did an analysis based on some anecdotal reports that the same people are repeatedly testing positive. We wanted to see if this is true. So we used the same two cohorts I just showed you, and they're measured at 3 time points. At baseline, they're enrolled, tested, and treated. We follow them up at time 1, and we follow them up again at time 2. And at each point, if someone tests positive, they're provided treatment with praziquantel. And what we asked is whether or not we see more people who are repeatedly infected, have 2 consecutive infections, than we would expect by chance alone. And you can calculate an observed over expected ratio. So you expect, if you have some distribution of disease in the population, you'd expect some number of people by chance to have 2 consecutive infections. We essentially asked, do we see more than we would expect? So if this observed to expected ratio is 1, there's no extra infections. If it's less than 1, there's perhaps some evidence of acquired immunity. And if it's greater than 1, we're seeing that some people are repeatedly testing positive. And in fact, that turned out to be the case. And particularly in the re-emerging areas, we found about 5 to 6-fold more people with repeated infections than we would expect by chance alone. When we account for exposure using a machine learning algorithm, that came down. That estimate came down to about a 2-fold increase in the number of repeated infections by chance alone. And in the other cohort, the cohort that started with very high infection prevalence, we still saw more repeated infections we expect, but not quite as many as in the re-emerging region. When we looked at this summer, we tested these people. These are the results I showed you. And we tested everyone again in the fall. We again treated everyone who was positive for infection. And one of the remarkable things is that, 1, we found infections 5 months later. And 2, almost half of the people that tested positive for infection in the fall had tested positive for infection in the summer. Which raises a question of why these people are repeatedly testing positive. It's possible that people who repeatedly test positive just have high exposure, right? It's the farmer who goes out there and gets infected every time. We tried to account for that in our model, and we still found an excess of repeated infections. I don't think that's the whole story, although it's certainly possible our exposure model is not perfect. Another possibility is host susceptibility, that some people are just naturally more susceptible to infection, and that may have to do with something as simple as the thickness of their skin in terms of how the parasite gets in, or a more complex immune response to the parasite once it invades. The part we're interested in is failed treatment. And failed treatment could have many components. There's been some new studies out showing that praziquantel dosing is perhaps not being administered optimally, that people are often administered a single dose, and it may be more effective if it's divided over 2 doses. You imagine from a treatment perspective, this is more complex. Obviously, there's a possibility of drug resistance. Drug resistance has been demonstrated in the lab, and Schistosoma mansoni has evolved drug resistance to a different drug that was phased out. But at the population level, we have not found evidence, and we, meaning the global health community, has not found evidence of drug resistance to schistosomiasis, although that's certainly an area of interest because there's really one drug. And the other concern is lack of adherence. Praziquantel doesn't taste good. It's not, while we say it's a single dose, people take a number of pills at that dose, and so we've heard anecdotally that people may save some of the pills for later. And it does make people feel transiently unwell. So we don't do directly observed therapy because people like to take it right before they go. There's possible, and this may be due to fatigue. In these regions, people have been treated for over a decade, repeated rounds of mass chemotherapy and then targeted chemotherapy. So lack of adherence is a real concern. So we can think about what would retained infections or this treatment failure look like operationally. And this is where the genomics piece comes in. If you think about a person who's infected with schistosomiasis, let's say they have two worm pairs, right? 4 worms that are reproducing, and those worms are emitting miracidia. Miracidia is what we're actually able to measure in the population. So you have a set of miracidia that are being excreted from one host, one adult worm pair, and another set from another adult worm pair. If we look at that person later, and let's say this person retains this adult worm pair after treatment for reasons having to do with noncompliance or drug resistance or what have you, these miracidia should be related to these miracidia. They're essentially siblings. They're coming from the same adult worm pair. They have a new infection. This should belong to a separate subgroup. When you look at time, at the early infection, they may have infections, miracidia unrelated to at follow-up because they cleared worm group A, right? But what we would expect to see is that if we do have evidence of treatment failure, you see siblings across years. So, yes. Yes.
So this assumes that they don't.
Yeah, so I mean, this is a really fundamental point that no one's really cared about until recently when we have the power to use genomics to answer these questions. So the conventional wisdom and the thing I was taught and we're all taught is that schistosomes mate for life. They're this beautiful couple that stays together forever. And there are a couple of thoughts about that now. One is they could just repair. They probably don't, within a single sampling period, you're going to see the same, they're not repairing within minutes, right? But they could repair. The other thing that could happen is treatment could kill one of the two. So you could have half siblings at the next time point. Yes, I think this is a fundamental point. I'd love to talk to you more about it because we have been thinking about this a lot. Yes, I think we now have the opportunity to try to answer some of those questions, which are not, which are based on kind of not a lot of evidence to date, Yeah. That's okay. Right. That way. So I'm gonna take us down the road and talk a little bit about the genomics tools we've been working on developing. And I should say this work has been done by David Pollack and Jonathan Short, who are here today. We have been working on developing a tool to really unpack these questions using high-resolution genomics. And we really have 3 goals. One, as much resolution as we can get. Much of the work to date has been done using microsatellite that provides us in the order of tens of loci. We're now looking at tens of thousands of loci. 2 is to keep the costs down so that we can analyze samples at the population level. This is not about analyzing 1 or 2 worms that we get from a laboratory strain, but really large numbers of miracidia. And 3, something that's feasible for the available life stages. And I'll talk a little bit about each of those as we move through. So the method we've decided to use is called dd-RADseq or double digest RADseq. It's a reduced representation amplification method that uses restriction enzymes to cut the DNA at conserved sites across the genome. It's a method that's relatively easy to roll out, and I can say this because I don't have to do any of the development. But the restriction enzymes are conserved across species, and we select for a certain size range. So cut the enzyme and DNA that fits a certain size range is amplified and sequenced. So to go through this in greater detail, the restriction enzyme we digest the DNA. We add a barcode so we can identify the DNA later. We select for certain fragment sizes. We select for the 300 to 600 base pair range. We do PCR to amplify the DNA so we have enough. And then we quality check the library, run it through high throughput sequencing, and then map the reads to the reference genome calling variant. One of the challenges in doing this is a limited amount of DNA available in available life stages. We cannot get worm DNA from people directly. It's invasive. It would require surgery. It's not ethical. What we get instead are muricidia. We put stool in water. If the stool contains eggs, the eggs hatch, and they float to the top of an Erlenmeyer flask. This is very glamorous work that Will and I have spent many days in labs doing this. But you can capture the muricidia, and you can actually put them on Whatman FDA cards, which are intended for long-term. The nice thing about this is we can archive samples at room temperature. We don't need a cold chain. We don't need any specific, sub-zero freezers. And as long as we keep them dry, we can keep them for a long time. The challenge is there's only about 1 to 2 nanograms of DNA per muricidia, so we use whole genome amplification to generate enough genetic material to do RADseq. So these are some of the results that from our early method development. This shows the proportion of expected genomic fragments by size on the x-axis here. That we have recovered, and the proportion is estimated using an in silico digest. So this is with adult worm DNA that we obtained from an NIH lab that provides Schisto resources to investigators. This is from a single muricidium. And what you can see is we had fairly good recovery within our target size range at 10x blue, 20x in green coverage. And just to show the same data in a different way, we get about 10,000 loci in our target size range for each muricidia. And the good news is when we did this with multiple muricidia, we get very similar results. Replicable. This was just recently published with Jonathan as lead author in PLOS neglected tropical diseases. We're really happy to have that out. We've run this, when we did the method development, we worked with samples from 2010. We've more recently been able to do this in 2007, so it seems to be a method that's working for old archived muricidia. We can call about 100,000 variants from about 10,000 loci, and the cost right now we're estimating is around $70 to $100 per sample. We're hoping that cost will continue to come down on the natural decline and sequencing costs, the decline in sequencing costs overall, and then some efficiencies. One of the things, back to our question of retained infections, this shows muricidia collected from 7 hosts in 2010 in a single village. So each human host is indicated with a number. This is host 1. And we're looking at the relationship between muricidia using rare allele variants. And what you see in these dark lines are siblings. So individual 7. We have 3 muricidia that appear to be siblings. We can presume these muricidia came from a single adult worm pair. similar. For individual 4, we see 5 individual myristidia that appear to be. I'll return to some of the more puzzling things here, but just to go back, so we think we're seeing all these are coming from a single worm pair. These are coming from a single worm pair. Individual 3 appears to have multiple adult worms. We didn't comprehensively sample each individual at this point, so we can't say the maximum number of worm pairs they have, but we can estimate the minimum number. This is all kind of pilot data. And then we looked in another village, 2 individuals, and again, this individual appears to have siblings, but what's interesting is the circles are from 2008, and the squares are from 2010, and what you can see here is individual 1 appears to have siblings across years, which we think is evidence for a retained infection. However, you will notice a couple of things that surprised us, namely that individual 1 and individual 2 appear to be shedding myristidia that are siblings. We think this can be explained because they're double cousins, and David and Jonathan and I have spent infinite amounts of time thinking about all sorts of scenarios of inbreeding, and I never thought, but double cousins is a situation that if my husband and I have children, and then we introduce our respective siblings to each other, and they have children. So my brother marries my husband's sister. Those are double cousins. And they appear to be at the surface similarly related as siblings, although if you can look at longer reads of the, I think we can untangle that, although that's kind of our ongoing puzzle. And again, this gets back to this question of, are we seeing monogamy areas? So, area of ongoing investigation. What we think we can say with some certainty is there is evidence that people are repeatedly testing positive, and with less certainty we can say we think that treatment failure may be occurring due to retained infections, although we want to do more work on this. The big question is, is this drug resistance? Is this non-compliance with treatment? Is this suboptimal dosing? We don't know. That's an area that needs to be investigated. So our second question is really, where are new infections coming from? So if indeed we can say that an individual has a new infection in these hotspots, where are they coming from? And conceptually, you can think about it this way, that you have, let's say you have a new infection here. You could think about the source of infection as being migrants, right? So they could be coming from some sort of outside source into this population. Or you could have it be a local infection. So let's say we treated everyone in a village. We see infections, a new infection at a follow-up time. It could be that came from outside, but it could also be it came from inside, right, and that we didn't fully clear the infections. And that local population can be defined at the village level or at a cross-village level. You could have multiple villages all kind of trading infections across a network. And it's important to note that if we did, if we think about infections at a local level, you could have multiple populations. You have human populations, and you can have animal populations. Schistosoma japonicum, unlike the other 2 major species, can infect an array of mammalian hosts. And so you could have either directional, bovines as a source of infection, perhaps because they weren't treated, or humans as a source of infections for bovines, for that matter. So we've started to unpack this question. I'll say our answers to data are fairly incomplete, but I'll tell you kind of where we've been and where we're going. One is just using 7 samples in our pilot data that was published in this recent paper. We had 7 myristidia from 3 people in 2 villages. We did a principal components analysis. For those of you not familiar with PCA, it's a way to reduce large amounts of information to So if you look at the first principal component here, it readily sorts people by village, sorts myristidia by village. So these myristidia village B, and these myristidia A. If you look at the second principal component, it's sorting myristidia by people. So there's some sort of population structuring here. We looked at a larger sample of 88, first using an analysis package called Structure, which is which subdivides the population to an optimal number of populations and assigns each Myristidia to a probable source population. And you can see some sort of sorting, particularly Myristidia from high appear to belong to one type of population, whereas population, again, when you do principal components analysis, it sorts the populations by villages. Each color is a different village. These two villages here, because they're quite interesting. This is a sibling analysis of these, or a relatedness analysis of these two villages. We sampled, we have Myristidia from one individual in village F right here, collected in 2008. Myristidia from two individuals from village E right here, collected in 2010. And what's quite interesting is you can see some very close relationships between these two villages. These villages are about a 30-minute walk apart. And I was going through my notes this morning, and I realized we walked from this village to this village when doing a field data collection in 2010 because the road was out. And people are saying how there's many close ties between these two villages. And in fact, there's a school here where kids from this village go to. So it's quite conceivable that these villages either operate as kind of one mega transmission zone or villages from infections from one villages are being seeded into another. This idea of transmission networks is an area of great interest to us, and this is a paper that Jennifer Head published with Justin Reme's group out of Berkeley that I helped with, that is looking at the directionality of snail population movement. So they use satellite analysis of snails that are the intermediate host for schistosomes to ask really whether you see evidence of sources or sinks of snails across distances. And you could think about for snails, distance might be just how far it is or how wet it is along a path or whether there's topography. So you evidence that some villages serve what we're hoping to do is extend a similar analysis to our data, but using much higher. So I just have a few more things, just kind of where are we going next? One, we really just want to clarify the extent to which treatment failure is occurring in these villages and serving as a source of new infections. So not only are people retaining their infections, but are those retained infections serving to populate? And this really requires digging into this issue of relatedness and getting at the issue at potential clonal infections, which we're looking into, and we're hoping to analyze in the short term in the hundreds of Myristidia. In the long term, we put in a proposal to analyze thousands of Myristidia. We've been archiving Myristidia since 2007, so we have a fairly large archive. The other thing we're really hoping to yes, go for it. Question. I don't know the answer to that. I think it's something. One of the tricky things with schistosomiasis is people aren't seeking care for their infection. So when we go in, we usually go in annually or every other year. So it's possible if we're measuring every 2 years, what looks like a new infection to us may have occurred a year and a half ago. And I think that's the challenge. Like, I think to do that type of analysis, we'd have to go in much more often and measure infections. So maybe worth doing. Yeah. But it could be a nice way to pair the two.
there's a dynamic. That they don't get infected.
Yeah, and I mean, I think that these are the kinds of questions, because the global health community is rolling out a very treatment-focused strategy. We think we are doing the right thing, and by we, I mean we as a global health community writ large, by treating people. But it's worth asking, you know, what happens when we treat people? How quickly are people repopulating? Are there people who are particularly susceptible that are that need repeated treatments or some sort of other strategy? I mean, I think that's exactly what we need to be doing. So, yeah, the other area of interest is obviously to look at the spatial patterns of infections and the role of local reservoirs versus importation in transmission hotspots, both looking at animal populations and over space, and thinking about space not just in terms of how a parasite or a human might travel. So in conclusion, you know, we definitely see persistence of schistosomiasis in these hotspots, which we originally thought we'd be looking at for years. We're now looking at them a decade later. Hopefully, these are the last stutterings of schistosomiasis in China. We don't know that to be the case. I will just remind you, because I gave a similar talk a month ago, and everyone said, wow, there's a lot of schistosomiasis in China. There's not a lot of schistosomiasis in China. We are going into what we think are the last remaining hotspots. But I really think these genomic tools offer the potential to ask questions about the feasibility of elimination and why, despite all these aggressive disease control programs, we're seeing. I think that merging our epidemiology and genomics work offers the potential to evaluate questions such as whether treatment failure is occurring, what the importance of parasite import is there evidence of selection? So starting to look at the genome and asking, is there selection either for drug resistance or some sort of evolved reproductive, you know, more or less egg output in response to pressure? Is there, and then finally, you know, what is the role of these non-human reservoirs? From an ecological perspective, it's interesting to think if we put all this pressure on humans as schistosome hosts, is the parasite going to find another population? So I just want to acknowledge the many people that contribute to this work. The Sichuan Center for Disease Control and Prevention has been my collaborator since 2006. They have been an enormous source of support. They have this incredible field team, and just to show you, it's no joke to do test 3,000 people in 36 some odd villages in a hot summer, cold fall. And I wanted to thank my collaborators here, David Pollack, Jonathan Short, Katerina Kekris, and Will Eaton, all of whom have, Will spent, 2 months in China at least this summer, 3 months in China this year, really helping make sure our field work went smoothly. Todd Casto at the University of Texas at Arlington has helped with some of the sequencing work along with his students. BEI Resources is an NIH repository for schistosomiasis materials, Sichuan CDC, and of course, my mentor at the University of California, Berkeley, Bob Spear, and Justin. So, I just wanted to leave you with this image that I found as I was digging through my photos. This, I don't know how well you can see it, but these are rice paddies here. And this is the approaching our reemerging areas. And I think this is, you know, a picture that's quite relevant to schistosomiasis in China. I think if schistosomiasis is eliminated in China, it's going to be eliminated because China has the resources and socioeconomic growth is such that they're able to essentially pave over all snail habitat, which is what Japan did to get rid of it. But I think there's also a number of challenges you can imagine here as the urban-rural divide just butts up. With that, thank you for your attention, and I'm happy to. Yes. that's a fair question. What I can tell you about the snails, which will not directly answer your question, we started in 2007 looking at humans, bovines, snails. We collected, I think it was 3,000 snails in the summer, doing this very systematic survey every 10 meters in snail habitat in these reemerging regions, where we found a lot of human infections and bovine infections, and we found one infected snail. And we were so surprised by that, we repeated that again in the fall because we thought perhaps the counties had done some sort of treatment right before we got there and killed off a lot of snails. And we had the exact same results in the fall. Infected snails are out there. We think once they're infected, the lifespan of the infection is as long as the lifespan of the snail, particularly because it decreases the snail life expectancy. But we are having a very hard time finding infected snails. It's actually a problem we're having for another parasite in Thailand as well, where once infection prevalence is kind of below some threshold, they're very hard to find. I don't know that that's the case, or it's just a probability game. All you need are a couple of infected snails because they can emit one infected snail can emit hundreds of cercaria per day. Is that enough to sustain? Which comes back to our questions of clonality. As the cercaria coming out of a single snail are all clonal. Theory. So, I mean, part of the repeated infection analysis that we did, we theoretical modeling thinking about host susceptibility. So not taking the immunological standpoint, but more the mathematical modeling standpoint. And it's certainly conceivable. And a grad student who came after me in the lab I came out of did a fair amount of his dissertation work thinking about what role host susceptibility might play. And if it's there, it would make an impact and possibly explain some, but not all of what we're seeing. But we haven't done is the parallel analysis to look at. So it's certainly an issue. We have some co-infection data with other helminths, which is the easiest to do, test for them in the same way. We haven't found a lot of signal there, but area of interest. I mean, it's actually an area of interest from a pragmatic perspective because China, unlike elsewhere, is so focused only on schistosomiasis. Part of our thoughts is also if you're going to go out there, treat people, you may as well think about at least the other soil transmission. I mean, so the mathematical models are all based on assumptions. So you assume some sort of exposure profile, which is data-driven, and then you can just add in kind of a susceptibility component that there's some distribution of susceptibility in the population. It's all based on assumptions. So we've been testing, I didn't show any of the animal data, but we have been testing bovines as well since 2007. And we're seeing a lot of infections in bovines, including there's been a big push to get rid of bovines. Yeah, we haven't tackled it just because we've limited resources. We just put in a grant to try to tackle not only the bovines, but also out and sample other. So, it's what a lot of people do, and there's some papers out there suggesting that bovines play a big role. We were really surprised by how local transmission appeared in our data, and actually are starting to think, without having seen the other side of the data, that there does seem to be a lot more relatedness in the human data than perhaps more driven by 1 to 2 per household. So that could be a source. So, which is why we want to dig into this further. And, it also could be kind of a game of whack-a-mole. You get the bovines, and then you... So we do active surveillance. So there is a passive surveillance mechanism, which is when someone who has never been exposed to schistosomiasis, only a subset of those people, gets schistosomiasis, will have an acute reaction. It's called acute schistosomiasis or Katayama fever. That will cause them to go to the hospital. They get very high fever. They're very sick. In China, they've used that to look for new areas or areas where it's reemerged. And that's what triggered some of those initial reemergences. Our work suggests that's really not. That's really just. But a question that is ongoing is kind of how do you do surveillance? People get tired of submitting stool samples all the time. Not gone, and people get tired of analyzing them. But if it's not gone, there needs to be something. That's what we aim to do. Actually, so there's 2 ways to test for schistosomiasis. Yeah. So there's the WHO standard for testing for schistosomiasis is collecting a stool sample and putting. There's some small amount of stool on a slide and looking for eggs. At infection prevalence at the level we're seeing, that's not sensitive enough. So we collect stool on 3 separate days. We use the Cato-Katz method, which takes a small amount of stool. And we also use the Chinese method, which is called the Mirror-City hatch test, which essentially filters the stool, puts it in water, and looks for a Mirror-City that hatched and floated to the surface. But diagnostics is a China is relying a lot on an immunoassay. There's been a big push to standardize that immunoassay. Yes. I think how to say this tactfully. We work with 2 counties primarily where we're hoping to expand that further. One county, I think, has the right environment for schistosomiasis. Our other county, which I love working with, they want to go out for nice dinners and party. And I really think that explains some of the transmission. That I think like the health infrastructure has to, and I'm overstating this, and I shouldn't say it quite so bluntly, but I think there's a lot to be said for the regional differences in health. And if you have a really strong on-the-ground team that's doing control. So I do think there's variability. In this region? A big study looking at night soil use, so the use of fertilizer. And we definitely see more infections in villages where more people. Village level risk factor, not an individual level risk factor, which makes sense. There's a big push in this region to move people into housing with communal biogas digesters, which are a sanitation system that generates methane that you can cook with. And it's possible at the commercial level, at the large level, those biogas digesters will inactivate the eggs. There's a lot of lab studies showing it'll happen. We're not sure it's happening as well in the field. that's a positive sign. People in our villages have household level biogas digesters, and we didn't see any. I think it's just because there's not enough waste, not enough heat. Yeah, I mean, I was talking with Sichuan CDC about this. I mean, I think the most obvious thing is people are retaining infections. The very least what we could do if someone tests positive is treat them, retest them at some defined interval afterwards, and make sure, test and treat until the infection appears to be gone. There's some fear that the parasite will be damaged, stop shedding worms, and then so you'll test negative, and then it will start shedding again when it repairs itself. Method, but that at least is a place to begin, and that has real implications. The other thing is to think about a 2-dose treatment strategy instead of single dose.